The ARPANET program was the predecessor of the internet as we know it today. It was led by a company called BBN Technologies. They built that network to send packets of bits from one point to another, but they had no way to imagine what the internet would be used, say 70 years, 80 years down the line. The Center for Quantum Networks is aiming to build the quantum internet, the internet of the future, which will be able to communicate qubits, packets of quantum bits of information from one computer to another. Quantum information is extremely fragile. It does not propagate long distances without destroying itself. In order to regenerate quantum information, you have to build quantum repeaters. Quantum repeaters are special purpose quantum processors that have quantum memories, interfaces that can have qubits that are sitting in the memories go out in the photonic form and vice versa, and a stack of error correction and networking protocols that go on top of that. One of the biggest challenges of building the quantum network is to design and build that quantum repeater and put it together with the entire protocol stack that will be able to run the various applications that will benefit from this new service called quantum communications.
The way that the Center for Quantum Networks is pushing the limits of quantum information science is organized into 4 thrust areas. The first thrust looks at the protocols and the theoretical modeling of the quantum network. The second one focuses on the architectural challenges of the subcomponents like a quantum repeater. The third is on the physical layer, quantum memories, interfaces to photons, quantum frequency conversion, and the fourth considers societal impacts.
The impact on society is still a bit unknown. I mean, we're really hoping for some huge benefits in communication security, medical applications, the medical field, financial transactions. We've recruited what we call Quantum Society Fellows, and these are researchers across the whole world who have proposals that look at particular aspects of the way that one or more quantum technologies is going to affect society.
At this point, there is no infrastructure for propagating, generating quantum information, and passing it on to users throughout the world. It's incredibly challenging to do that, both from the physical perspective, but also from my perspective as far as what the protocols should look like. And so it's just a very exciting problem domain to be working in.
Here at the University of Arizona, the testbed is responsible for coordinating and integrating different research efforts across the whole sequence into a functional quantum network and test the key functions for future quantum networks. The partnership between industry and academia is very important. We are talking to many different industry partners to learn about their needs. Some partners are more interested in quantum sensing applications. Some are more interested in quantum communication or secure communications. Some require a near-term application, but some are more focusing on the long-term quantum network development. Based on the discussion with industry partners, we can better tailor our application. Also, our industry partners are helping us developing very key components for the quantum network. For example, we are partnership with some vendors to develop power-efficient, compact cryostat to host the color sensors. So these components will be very critical to improve the overall performance of our quantum systems.
One of our workforce development programs is the master program, the MS Quizy, and this is an example of why it is really important to go beyond building the entry-level workforce. It's even more important that you do this in an inclusive manner, and the CQN MS Quizy at the University of Arizona, that is an example of how we're trying to achieve this. We can look to recent history and we can look at many missed opportunities in workforce development, specifically semiconductor technology. In general, we can seek technological advancements in which whole populations have been left behind in terms of workforce development. Here in quantum information science, we really not only have an opportunity, but an obligation to ensure that the future quantum workforce is one that is representative of the changing demographics of this country. They need to be able to work in teams, interdisciplinary, in a way that exceeds our current demands. In the same sense, they also need to be aware of societal impacts of their work in a way that is completely new to all of us. And this awareness of future demands, that is really foundational to our program development. Our CQN outreach initiative is called SPARKS, short for Sparking Curiosity in Quantum Science. It's something we started in the spring of 22. Our main goal with Sparks is really to introduce broader audiences to the world of quantum science. We take the word outreach very literally, meaning we want to really reach out. We go to schools like other outreach programs do. We participate in STEM events. We also bring quantum science to locations you would normally not expect to find STEM. So we're really using these opportunities to very intentionally reach out to populations who are underrepresented in STEM. It's really an essential part of our workforce development because our students and also faculty are able to participate in these outreach events. And so Sparks allows us to bring our message out, to introduce people to science, but also to train ourselves, the scientists, on how to best deliver science.
At the University of Arizona's College of Optical Sciences, we are building a new building called the Grand Challenges Research Building. The fourth floor of that GCRB was completely designed by our faculty members and senior postdoctoral scholars to house the various aspects of the Center for Quantum Networks. This building will also facilitate external collaborators, for example, from MIT, Harvard, Yale, and many of our other partner institutions to come out on extended visits and sabbaticals. The Center for Quantum Networks is the first organized effort in the country that brings together all of the disciplines and all of the know-how that will be necessary to build this entire stack of technology. CQN has the potential to be the effort that really for the first time develops the core technologies that are at the heart of the future quantum internet.